And we're live.
And we're live. Okay. Well, for those of you watching with the video, welcome back to ENSO seminars. As usual, we're gonna wait 5 minutes or so that any people that want to watch this live have a chance to join the channel. And in the meantime, we'll just hang out a little bit. Yeah, if you're interested in giving a talk, send me an email or send Marek an email. We've got talks scheduled. Let's see. Got talks scheduled through until May right now. So maybe you'd be interested in giving a talk in June or July or something. Give me a shout.
What kind of people are you looking for the talks?
You name it. So we've had some people speaking from the enactive community. We've had people presenting models, but it would be great also to have some more ecological psychology people, for instance, giving talks. That would be great. Marek's talk was not a modeling talk per se. It was more of a talk from a psychologist, and hopefully we'll have some philosophers speaking later in the year as well. So we like it all, as long as it's related to feedback loops and intelligence and cognitive science and behavior and so on. Okay, we've got a viewer here going on. For those of you who are viewing, if you notice anything going wrong with the presentation, if I don't know, the sound's cut out or anything like that, please do send me an email or an instant message, and I'll be watching that during the talk, and we'll try to respond as quickly as I can.
Same thing, yeah. With the talk, I'd be happy to repeat if there's a little blip in the bandwidth and something gets cut out.
The Google Hangouts on Air has been pretty good with that so far, so I'm pleased with that. The only thing that still really isn't working is the videos. For whatever reason, the embedding anyway of like YouTube videos is still doesn't seem to work properly. But in our last talk, Nathaniel was able to stream some videos at a relatively low frame rate, but he was able to stream some videos for his talk. So hopefully Google Hangouts on Air will fix that soon. Okay, I'm going to go top up my coffee, and I'll be back in 2 minutes. We've got a few more viewers now, so that's great, and we'll probably start in 2 to 5 minutes.
Okay, this is just recording.
That's right. It's just recording now, and people will probably want to fast forward. So in the YouTube video, I'll put a link just beneath the video, which will say fast forward to 6 minutes into the video, and it will let people skip all of this stuff if they want to and cut right to the start of the talk.
Okie dokie.
So you just got a nice live recording of Eran there waiting for the talk to start.
Oh.
Okay, we'll give it another couple minutes. Does that work for you, Eran?
Okay. I'll try not. I'll resist picking my nose in the meantime.
It's interesting. It's showing sort of viewers popping in and popping out, and I don't quite know. Maybe people are having technical issues. I don't know.
There will be a talk for those checking in right now. Where do I see? Do we see who's here?
It says I don't know if it shows it in your screen, but in the bottom of mine, it shows in the bottom right-hand corner the number of viewers.
I guess that you have more information as a moderator.
Maybe. Okay, for those of you just joining us now, we're just waiting, giving people time to join the video. And so just hang out, and we'll be with you in just another minute or two. Do you want to engage your screen sharing, Eran, just to make sure that that's working?
How's that?
No, I don't see your.
No. Oh, okay. Here it is. Oh, yep. Screen share. Stop. Start screen share. Whoa. Have a little bit of a feedback. There's your feedback. Okay, and to slideshow. How's that?
Yeah, it looks great. Looks perfect. Okay, let's get started if you're up for it.
Okay, let's. Oh, yep, I'm ready. I'll go back to my camera.
Great.
There we go.
Okay, so welcome everybody to the fourth ENSO seminar. Today I'm very pleased to be presenting Eran Agmon, who's going to be presenting some work that is related to or similar to the work he presented at ECAL. I guess last year, 2 years ago now. Now that it's
actually just this last summer.
Was it?
Yeah.
Okay. Yeah, just last summer. And so Eran did his Bachelor of Science in Cognitive Science at the University of California in San Diego, and then a Master's in Systems Science at Portland State University, and is now wrapping up his PhD under the supervision of Randy Beer. And the title of his talk is Ontogeny and Adaptivity in a Model Protocell. And if you could take it away, Eran, that would be great.
All right, so on to screen share. And move this aside. And here comes the presentation.
If I could just interrupt for one thing, just to remind people that if you have questions that you want to ask during the seminar, the best way to do that is probably by way of the ENSO seminars presentations page for this talk. The other possibility is using the Q&A app, which is perhaps part of the window that you're watching this video in now, but that hasn't worked for everybody. So maybe the best thing to do is to just ask it by way of the forum on the ENSO seminars website. And I will read through that at the end of the talk and relay any questions that you have there to Eran. Okay, thanks Eran.
Okay, here we go. So I'm presenting work I did in collaboration with Alex Gates and Randy Beer in Indiana University. Start off with an outline. I'll begin by introducing a model of emergent individuality, or a protocell. From there, we move on to obtain a network of possible ontogenies for this protocell, and then analyze this network structure according to its ontogenies and the morphologies that are reachable. And finally, at the end, I will quantify viability and adaptivity and demonstrate it in the model. So here is the model. I've given entire talks on just the details of how this works, but we don't have time for this here. So if you're interested, you could read these two papers listed at the bottom of the screen, or ask questions at the end of the seminar, and I'll be happy to answer. But to give a brief summary, we have 4 chemicals that diffuse across this lattice: autocatalyst, membrane, food, and water. This is a concentration-based model. So each lattice site has some concentration of the 4. On the left side, I'm just showing the chemical with the highest concentration, but each lattice site actually does have all 4 of the chemicals present to some concentration or another. These operate according to dynamics. These are continuous dynamics, so it's not a cellular automata as I have here. Again, very, very quick overview of the dynamics. We have reactions in which 2 autocatalysts in the food molecule make another autocatalyst, and likewise 2 autocatalysts in the food molecule make a membrane. There's diffusion, so these concentrations diffuse freely across the lattice. There's repulsion, which is used to mimic kind of oil-water phase separation, but between the membrane molecules and both the autocatalyst and the water molecules. We have decay over here, so autocatalyst and membrane decay to zero. There's food that's refilled at the boundary and diffuses in towards the center of the site. And finally, membrane has an orientation which allows it to mimic phospholipid bilayer type behavior. Okay, now I'll give you a quick showing of how these dynamics play out. So here I've set up an environment that's filled with food. That's the green, and membrane and autocatalyst are randomly arranged in the middle of this lattice. Water is also present, but I'm not showing it for clarity. Okay, so here I'm going to play it out, what happens. Quickly, there's reactions. Food is eaten up. The oil and water separation between both the membrane and the water and the autocatalyst lead to these clumping-like behavior. We continue, the food continues to be eaten up. Now remember, it's being refilled at the boundaries and diffuses in, but decay drives these chemical concentrations back down to zero, and soon afterwards we reach what we call a uniform attractor, in which membrane and autocatalyst have been depleted, and the entire model goes to a uniform equilibrium of just food and water. Now, most initial conditions of the model go towards this, but we're not interested in uniform equilibrium. We're interested in a different set of equilibrium points called stable configurations. Now, I'll show you how that happens. So if we initiate the model in this kind of an arrangement, it unfolds. Now, the time scale here is much longer than the time scale of the previous sequence of snapshots. This is taking much longer, and it unfolds and unfolds. And then at some point, we do stabilize at a stable equilibrium point. So this is an equilibrium point in the dynamics, but that does not mean it's chemically static. It's actually, there's diffusion going on. So food is constantly diffusing in from the boundaries towards this protocell. There are reactions, there's decay, there's repulsion between the membrane and the autocatalyst and the water and the surrounding. And what allows this thing to stabilize is what we've called metabolism-boundary co-construction. So the autocatalyst concentrations are constantly making membrane, which diffuses and refills the concentrations on the boundary, and the membrane, by way of repulsion with the autocatalyst, keeps the concentrations, these internal concentrations, high enough that the reactions can keep on going. Now, the system would remain like this indefinitely if it was left unperturbed, but since this project was interested in ontogenies, we're going to introduce a slightly richer environment which consists of perturbations. And I'll show you this environment. So what we do is we pick a focal point on the protocell and then add some amount of concentrations. There's 4 possible magnitudes. So here, this focal point aligns with the focal point of this Gaussian, and we just add concentrations to it, either a whole lot or less. So we can do this at 9 different points that are determined by this grid. So we put a grid, and then there's 9 focal points, each of which can receive some amount of concentration. This happens to either the membrane or the autocatalyst fields, bringing us to a total of 72 total possible perturbations with the uniform probability distribution over them. So at any event, we pick one of these 72 perturbations and apply it to the protocell and see what happens. Now I'll show you what can happen. There's 3 classes of response to perturbation. In this first one, this is our initial protocell. We apply a perturbation to this top left corner, and after a short transient, it restabilizes at the same previous configuration that started off with. This is what we call a robust transition. The second option is shown here. We apply perturbation, this time in the middle, but this could again be anywhere. And after a short transient, it restabilizes at a different stable configuration that also engages in metabolism-boundary co-construction and maintains its organization through that. And the third option, shown here, is a destructive transition. So we apply perturbation, and the transient causes a breach in the membrane. Autocatalyst spills out very quickly, so it becomes very flat. The membrane can no longer be constructed, and after some time, it decays towards that uniform equilibrium in which there is no membrane, no autocatalyst, and the entire model is filled with a uniform distribution of food and water. So this is a destructive transition. Okay, now we're interested in ontogenies, which are defined as sequences of structural change. And I'll show you what I mean with one example of an ontogeny. So we start off with this initial configuration SC, apply perturbation, this time, let's say 28th perturbation, and this induces a plastic transition. Another perturbation induces a robust transition in this case. It's the same configuration, followed by another plastic transition, another transition, and eventually all ontogenies end up in the death state. It's just a matter of time and perturbations before this happens. Okay, so this was one particular ontogeny, and as you can imagine, if we had different perturbations, different sequence of perturbations, the ontogenies might have looked very different. Now, we are interested in the space of all possible ontogenies, and so to do that, we start off with the protocell and we expose it to all possible perturbations that it could be exposed to. These are the 72 perturbations that I listed earlier. Here, I'm just, this is a kind of a depiction. I'm not showing all 72, but we have some amount of perturbations producing robust transitions, some amount leading to destructive transitions, and then some to plastic transitions. Now here we see that there are 3 possible plastic transitions that this protocell can go through. Now actually, just for simplicity, I'm going to aggregate the arrows. So here, the width of arrows corresponds to probability of that transition happening. So the next step in this methodology is we take all the the configurations that were reached with plastic transitions, and we expose all of those to the same 72 perturbations and see what happens. So here we have new configurations are reachable. We have more robust, more plastic, and more destructive transitions. And we're just going to repeat this process of taking the new configurations and exposing them to the environment and classifying their responses. And this is how far we've gone so far in the search. So just to fill you in, this is where we started off with SC, and an ontogeny in this space is just a trajectory through this network. So a given ontogeny could be starting off here and moving through, and at some point coming to death. Now, I would like to point out these grayed out morphologies on the edge. These are just morphologies that we have not yet classified due to computational limitations. This model took a long time to run, and we just ran out of time. But we searched to a uniform depth of, I think it was 17 transitions from SC, and then at some point there was this exponential growth of reached configurations, and we stopped the process and focused our attention to the ones that we have discovered already. And this network that we've obtained has many interesting features. So to show its unique features and what kind of insights we can draw from this. Okay, next. Okay, so in the paper, we did several analyses, only a few of which I'll show you today. But we have a network structure, the analysis of the network structure. So this gives insights into the dynamics of ontogenies. We can look at the morphologies in state space and understand how these morphologies work. We can classify the perturbations and how the protocells' response to perturbation changes. Or we can also look at the underlying dynamics. This is a continuous dynamical system, so it has a phase space and basins of attraction and equilibrium points, and so we can also look at that. But if you're interested in these two bottom ones, read the paper, ask me later. I'm going to be focusing on network structure and morphologies for now. Okay, to begin, we're looking at network structure. So this is the same ontogenic network that I showed you earlier with the morphologies now just being depicted by nodes. I've also removed the death state, which was the outer ellipse earlier, and I've removed the unsearched configurations. This is a directed graph too, even though the arrows are not being shown. Okay, so what we do here, I'm going to show you how this has irreversibility, branching, and attractors. To begin, I classify it according to strongly connected components. So what these colored regions are showing are sets of morphologies that are mutually reachable from each other. So, for example, if you see my cursor, this configuration is reachable from this configuration and vice versa, and all the configurations within this region can be reached from all other configurations within this region. Now, this implies irreversibility. If we move from one strongly connected component, such as this one, to a different one, that by definition means we cannot return, because if we could return, that would have itself been one big strongly connected component, and it isn't. So we have a little bit of irreversibility there. We also have branching, and what I mean by that is if you follow one path between strongly connected components, you're essentially ruling out all the other ones. So if the protocell, which started off here, moved and went over here, it's ruling out all of these possible morphological states from its future. We also have attractors, which are sets of configurations that once you enter them, you remain there for the rest of your life, and the only way out is really to death. So these are attractors and dynamics. Now I'm going to show you that there's plenty of these kinds of transitions possible within this network. So we have a lot of irreversibility, and we have a lot of branching all over this system. Okay, that was the network-based analysis. Now we're going to move to a morphology-based analysis in which we only look at the states of the 154 searched configurations, some of which are shown over here. So each of these is a high-dimensional state. If we consider only the autocatalyst and membrane concentrations, it makes up a 3,200 dimensional system, in which each one of these is a point. To reduce that high dimensionality, we project the 3,200 dimensions onto 2 dimensions here, determined by isomap. This is kind of like a nonlinear version of principal components analysis. And all of the morphologies find a place within this projection. And then we classify it according to clusters detected by k-means clustering in this case, but you could do any clustering method. And we can observe, even just visually, we see that there's high clustering of morphologies here shown just by the different colors determined by k-means clustering. So each of these clusters has some number of morphologies that are close to each other in state space, and because of that, they also share some morphological features. Here, each cluster, for each cluster, we show a prototypical morphology. So we have these ones that have one bar. These ones are all have this more square-like shape, and they have two bars in the middle. We have some bigger ones, some ones with thicker bars, some lean to the left, some lean to the right, and we have all sorts of different interesting morphological features pop up which characterize these different clusters, which is kind of interesting. So we've seen clusters in the network, in the ontogenic network, and we've seen clusters in the morphologies. It turns out that these are highly, highly related. We can determine that by normalized mutual information. What that means is that when you are within a network type cluster, you also tend to remain within a morphological type cluster. And when you transition to a different network type cluster, you also tend to transition to a different morphological type cluster. And so you maintain, when you're within one of these, you maintain your morphological feature. At some point you bounce out, your morphology changes, and then you remain there for some time. Okay, the next analysis that we're going to be looking at is viability and adaptivity. So to explain what's happening, this is the same network we saw before. We have the morphologies that have been searched. The unsearched morphologies are on the edge, and then death is this outer ellipse. We've defined viability as average steps to death. So how long can a given configuration expect to survive? If we start off over here, it could undergo some amount of transitions. Here's an example. It can do this, and then that, and eventually go to death. Or it can do a different trajectory through this network and go to death. If we treat this whole thing as a absorbing Markov chain, we can analytically and exactly determine the average time to death from each configuration. So for example, over here, this SC, the starting configuration, has a viability of about an average of 3 steps to death. So there's, on average, it'll survive for that long, given across all possible ontogenies that it could undergo. Now we can do this for all of the morphologies. So here we have the viability of all morphologies, and we can see that there are some morphologies way far down in this ontogenic network, such as this one and this one, which have a higher viability than before. And we see quite a scattering of viabilities from 1 average step to death to 5 average steps to death. I should mention this is also a lower bound estimate because of these unsearched configurations over here. We've just assumed they transition to death in the next step, and likely that's not the case. Likely they actually have some higher viability, and that higher viability will increase the viability of all morphologies which lead up to them. Something interesting is also that the most viable configuration, which is this one over here, is not the most robust configuration, which means it doesn't have the most robust transitions. It's also not the most plastic. It's not the least fragile, but rather its viability is a consequence of how it's embedded within this network. So it has some a good amount of plastic transitions to other highly viable configurations, and that's what props up its viability. Okay, for the next step, we're going to be looking at adaptivity, which is defined as change in viability. So if we go from, now I'm looking over here on the left side, If we go from a less viable configuration to a more viable configuration, that's what we call adaptive. And that's going to be shown in blue. If we go from a more viable configuration to a less viable configuration, that's what we call maladaptive. And I'm going to show those in red. And here it is. So we have a fair amount of adaptive transitions here. It's about a little over 50% of the transitions that this protocell can undergo actually comes with an increase in viability. So given that it survives a transition and it moves from one configuration to another, that about 50% of the time will come with an increase in the expected lifespan that this protocell has, which is unexpected. This isn't a system that trivially gets weaker and weaker and weaker when it's exposed to the environment, but can actually expect to get stronger and stronger and stronger as it adapts and changes its morphology in a way that accommodates the perturbations that it's exposed to. Okay, that brings us to the end of the talk. In a quick summary, we took a protocell, put it in a simple environment, explored the space of possible ontogenies, analyzed several properties of this ontogenic network structure and the morphologies of this network, and then we quantified viability and adaptivity and showed it in the ontogenic network. So yeah, thank you very much for joining me. I'm also going to plug in a workshop that will be held this summer in A-Life in Cancun, Mexico, on the biological foundations of enactivism. So if you're interested in this kind of subject, we'd be happy to have you there and have you join the discussion. All right, that's it. Thank you very much.
That's great, Eran. Thank you. It was a great talk. And for those of you watching, you can now ask questions, and please feel encouraged to do so. How am I going to turn off this?
Okay.
How's that? There we go. Okay, now we're on.
Do you see me?
Go back and forth. So yes, please feel encouraged to post questions to the ENSO seminar website. We can, if you post them rapidly, then maybe Eran will have a chance to answer some of them now. Or again, you can use the Q&A app inside this window if you can find it. And while we wait, hopefully, for some questions from home, I do have a question or two myself. So if you're up for it, Eran, I'm curious why you chose to use this particular system rather than, say, like a Gray-Scott reaction diffusion system. Was there something really strongly motivating that? And if so, what was that?
So the Gray-Scott reaction diffusion system, which we actually saw last month with Nathaniel's talk, I think the same kind of analysis could expose some very interesting things in the Gray-Scott system. The reason we chose this particular system is because we had a previous set of papers that looked at in detail at the metabolism-boundary co-construction. Mm-hmm. So we were interested in how these different configurations can stabilize each other and keep each other together. And then we just developed this methodology on top of that model. But really the methodology is model independent. It could, as long as you have some kind of emergent individual, so an individual that can die and can change with perturbations if put in a different environment, you can still get an ontogenic network, and you can classify it according to the same types of properties that I showed here.
Mm-hmm. So how automated is that process? So if I wanted to apply this analysis, for instance, to the habits in my model, which I think is really interesting thing to do, subject these different patterns of behavior to perturbation and see how robust they are and so on in different ways. Do you have a program I can, I can just
I do have a program, but it is quite, it's built around this particular model.
Mm-hmm.
But the algorithm is really quite straightforward. You just need a way to classify a given configuration, or in your case, a habit. Mm-hmm. So you need a way to be able to copy it, store it, and then perturb it, map out everything that, all the different habits that it could lead to. And then you need to do some comparison to say, is this the same habit as before or a different habit than before? And so you're going to need to determine what makes the same habit. And that might be more unique to a particular model. Yeah. Mm-hmm. Mm-hmm. But that would be actually a very interesting analysis. I think it would apply nicely to a habits-based model. Yeah.
Another question for you. To what extent do you think that the results of your analysis, so these perturbations, the ones in this paper were all sort of took a Gaussian form. And if I remember correctly, in an earlier paper, you subjected a similar system to different kinds of perturbations. So I can't quite remember what they were. Maybe there was a noise one, which covered the whole field with noise. Yep. Maybe you don't have a definitive answer, and if not, maybe just your intuition I'd be interested to hear. But to what extent do you think that the results you have here are generalizable? So that if you were to give, do the Gaussian perturbations correspond to a whole class of other kinds of perturbations, do you think?
I think the results that we saw here, so that's the structure of the ontogenic network and let's say the degree of adaptivity and the irreversibility, I think that is unique to the particular environment that this protocell was exposed to, which is, as you said, these localized Gaussian perturbations in which I just add small amounts of concentrations around a given focal point. And you're correct in stating that this is a very, very small amount of the possible perturbations that it could be exposed to. And if I were to choose different perturbations, I'd obtain a different ontogenic network, would have different properties. And in fact, that's something that we have done. This is one of 3 ontogenic networks that we've uncovered so far. One of the previous ontogenic networks showed very low adaptivity. So we put it in this environment and it did kind of trivially get weaker and weaker and weaker and weaker until everything just died. And it was interesting that could happen. A different ontogenic network that was recently submitted for publication shows that even if we expose the protocell to a different environment, it moves through the morphology space in a different direction. So here we saw this kind of movement that we saw a few horizontal internal bars form, but if it was exposed to a different environment, and we show this in an upcoming paper, it can pick up different morphologies and actually diverge and explore a whole different region of the morphology space and have different network properties. And so that's something that's actually really important to address, to actually feel out the space of all possible ontogenies in a broader sense of what if the environments were different.
Mm-hmm. Cool. Okay, great. I think that's, I had one last question, and let's see, looking for other questions online. None posted yet, but I'm sure people will post some later online. We can answer them by way of text on the website. Mm-hmm. But one final question, and then maybe we'll wrap things up. The perturbations that you're applying are all these discrete, instantaneous perturbations of a kind. And I was wondering if you've looked at in this model the possibility of perturbations that are continuous in a sense, or actually, maybe more interestingly, perturbations that are environmental. So you talked about how the food is constantly diffusing in from the outside. I think that's the case throughout all of the simulations that you showed us today. Mm-hmm. What would happen, I wonder, if you were to starve the protocell for just long enough to the point where it starts to collapse, but then you give it plenty of food again or something? Huh. I wonder if there's a different class of perturbations, I wonder if the dynamics would be same. Just a thought.
That's definitely an experiment that one could run. I haven't tried that particular one before, but yes, the space of perturbations is absolutely enormous. It could include things like you suggest, which is drop the food field and then bring it back and see how that goes. We can have more. I think what you were getting at. There's two things you were getting at. You could have continuous time perturbations. So here I just hit it once and I waited for it to restabilize.
Yeah.
And I could actually have kind of an ongoing perturbation or perturb it during the transient. So before it even has time to restabilize, hit it again. And that in many ways is
right.
a more realistic situation. It complicates the analysis, but I think that's something that will need to be developed in the future. And then you also mentioned you could have more what I think you said environmental perturbations.
Yeah, thinking about the feeding rates.
The food field. Yeah, so you could have perturbations that actually come from within the model rather than this kind of top-down dropping things onto the system from above, and that's a different question. Which there you'd need to find a way to classify the environmental perturbations as well. So you need to have some kind of a classification scheme for what kind of perturbation it is, because what I've done is I've defined the perturbations, and so it's made things a little easier for me.
I see.
But that doesn't mean it's it's complete. It's there's a lot of exploration left.
Yeah, I guess one of the ideas that prompted the question was just thinking about again, going back to Gray Scott reaction diffusion spots. You see them sometimes respond to regulate their environment in the sense that they move up the food gradient, for instance. Mm-hmm. And I wonder if you would see similar like movement in your model, which is another form of adaptation, and so on. But I totally take your point that there's a huge number of perturbations you could subject it to, and you have to decide what to do. And I really think it's great that in a sense you haven't been intimidated by that. I think some people would say, "Oh my gosh, there's so many perturbations you subject it to; it's impossible." But
start small. Start with a few.
Yeah,
work your way from there.
Yeah, it's really good, really interesting stuff. Thank you so much for presenting today, and I hope you're going to be up for responding to questions that show up on the forum later. And thank all of you watching at home or at your office, and we'll see you next month. Hannah de Jager is going to be giving a presentation, which I'm also very much looking forward to. So thanks again, Eran, and goodbye, everybody.
Great. Thanks, everyone. Bye.